All right, so good morning, everyone. So for this second week of the course, we are going to be quite independent from what we did in the first week. We will just use the first week at one place to localize in a sense, but the techniques we are going to use are quite independent. We are in a kind of a different realm. And so for 2 lectures now, I'm going to talk about result called Bernstein von Mises theorems. So today is one. And today we are going to talk about functionals meant as mainly one-dimensional functionals. And tomorrow we'll go a bit beyond that. Okay, so let me, to motivate a bit these 2 lectures, let me give a practical motivation. So in survival analysis, so if you are a statistician working with medical data, it's often that you have observations, IID x1, xn, where you have some time, a certain event of interest, t, and it's possibly censored by some other variable. So I'll not talk much about the censoring, it's just that this is the typical, kind of the simplest survival analysis setting. Just to say that, so the quantity that people, so you don't observe directly ti, but only a censored version of it. So it's slightly more complicated than the density model, but still it kind of a bit similar in spirit. And what you are interested in is so either the distribution function of t or what's called the survival, which is just 1 minus the distribution function. Okay, so that's called the survival function. And another object you may be interested in is slightly simpler, is the median survival. So the median survival is f minus 1 of 1/2, the quantile a half. Okay, so that's a certain psi of f. Okay, certain functional. And so in practice, people often use the Bayesian approach here. So in the Bayesian approach, you put a prior on what you don't know. In particular, you put a prior on, say, the distribution here, for instance, or its density, if it has a density. And then what you do is that if you are interested in these quantities, you look at the induced posterior on either capital S or on psi. Okay? So what you would observe on the computer, so assuming that you know how to sample from the posterior distribution, the induced posterior distribution on this object. So for this, let me start with the second one. So this one is an element. So it's a one-dimensional functional, whereas this one is a function. Okay. So in the first case, in this case, what you would observe is, say, if you can draw from your posterior. Okay. So you have some. If I just sample from the posterior and I plot, say, the histogram, the empirical distribution I get, I may observe, and indeed, in many cases, the prior is well chosen, I observe something like this. If I draw, say, the empirical the histogram corresponding to this sample from the posterior, okay, so I will observe something which is very close to a Gaussian. Okay, so it suggests that maybe there is some asymptotic normality, like the posterior has maybe a Gaussian shape in this functional. Okay, so this may be interesting because then in practice what you do is that you then take often the quantiles. So here, let me draw the quantile interval. So what we can write called sometimes something like this. So the quantile of this distribution, the empirical quantiles, so sorry, alpha over 2 and 1 minus alpha over 2. Okay, and then for uncertainty quantification, here we have an interval I of x, and we'd like to know that it's from the Bayesian perspective, is said the natural interval here. Does it quantify uncertainty in the sense that it is a frequentist confidence interval? Okay, so that by definition this is a credible interval. Okay, it has 1 minus alpha, it captures 1 minus alpha of the posterior mass. Is it also a confidence interval in that, do I have something like this? Okay, P here under the true, say, F naught of psi, so this functional, psi F naught belongs to Ix. Does it go as n to infinity to 1 minus alpha? Okay, and in the other situation, it's a little bit more complicated because you'd like to estimate a whole function. Okay, so in practice, what you would do, it's not much more difficult in principle. If you can sample from the posterior distribution on F, on capital F, okay, or on capital S, so F is increasing, S will be decreasing. So if I draw many samples, so one sample would be like this, the other one like this. Okay, so those are samples from the posterior. So if I know how, by, for instance, an MCMC algorithm, if I know how to sample from the posterior on capital F, I sample many times, say 10 times or something like this, and I get what we could call a spaghetti plot, like, and then if I look at, say, for instance, 95% of the, or I have to draw enough times, or say, I can try to draw in a certain way, so maybe here not so good, a band here that captures most of the paths. So here maybe I can authorize just a few paths going outside, and I get a region here. Okay, and I'd like to use, say, to claim whether to answer the question: is this region, does this region properly quantifies uncertainty in the sense that is it a confidence band for S naught? Okay, and to have this type of things, we may ask whether there is a functional limiting result here in the background, perhaps, and if so, this may, if also it's optimal in some sense, it may give us optimality also of this band. Okay, so that there's a bit more complicated situation. We'll discuss that tomorrow. Today we'll focus already on, say, as a building block, already on one-dimensional functional, and that's already quite, that gives already quite some material to quite some interesting phenomena. So let me actually, so here I wrote two names, Bernstein and von Mises, but let me go back much earlier. So Laplace observed the following. So take a binomial model. Okay, and so for Laplace, it was already natural to be Bayesian, so he said, okay, let's take as a prior distribution a uniform distribution on theta, okay, and see what happens. And what he noted is that the posterior distribution looked like something. So here my observation is x, and here we get the something like this. Okay, and so, sorry?
X over n. X over n, I guess.
Well, no, here it's x over n. Yes, thank you. Sure, thanks. Perfect. Okay, so here I put a little star just to remind you that the Gaussian distribution was not yet invented at the time. So actually, Laplace observed that the distribution function corresponding to the posterior goes to the distribution function of a distribution whose density is e to the minus x squared over 2 divided by square root 2 pi. Okay, so afterwards, nowadays we can remove it. Okay, so it seems that there is a kind of central limit theorem, some asymptotic normality result here at hand, and so you know this is not an empirical mean. This more complex subjects is a conditional distribution, and can we prove in some generality some result like this? Okay, and this is what Laplace, Bernstein, von Mises theorems are about. Okay, so let me talk about the parametric case first. Okay, so suppose we have a parametric model, IID data, and capital theta, say, in a P with P fixed. Okay, I discuss essentially P equals 1 just for simplicity. Well, I'll set the result in RP, but okay, we can, if you prefer, you can think in dimension 1. So let me introduce the log likelihood. So again, as usual, we take a dominated model, okay, and to have base formula. And P is the density, and remember that everything depends on n possibly, but I forget the dependence in n. Okay, so assuming you can take derivatives, let's just introduce the partial derivative with respect to theta of L theta. So actually, you can weaken this even a little bit, but I'll not talk much about it. Suppose it exists, and suppose you can write it's the expectation of, so there is a dot here, L theta dot, so that depends on x, L theta dot x transpose. So this is a matrix called, generally it is called the Fisher information matrix. Okay, so I have here a data x1, xn. Okay, so in the frequentist sense, they are distributed IID according to some p theta naught. And we'll say that the model P is LAN, so for locally asymptotically normal at point theta 0. If for any h in, say, in P, I have something, the log likelihood has a certain expansion, which with a quadratic term and a stochastic term. Okay, so we are in the IID case. So let me write the product P theta naught plus h over square root n P. So those are small p's. Okay, equal to. So let me write first I'll write the quadratic first. A half h transpose I theta naught h. So this is a quadratic term in terms of the h. So you expand locally around your parameter theta naught, for instance, in a certain direction h. Okay, and then there is a stochastic term. So plus 1 over square root n h transpose sum L theta dot xi, and then plus little op theta naught of 1. Okay, and today I'll write just as a shorthand pi 0 for pi theta 0. Okay, so when we look at this, we see that it's kind of an expansion of the log likelihood. And so why is it called locally asymptotically normal? So in fact, you can check, I'll not do it, but you can do it as an exercise, that if you would take a Gaussian shift experiment, like this very easy n theta 1 model where you want to estimate theta, and you do this expansion of the log likelihood, you get exactly this without the little OP term. Okay, so this beginning of the expansion is exactly the whole part of the expansion in the Gaussian case. Okay, the Gaussian shift experiment case. Okay, and so then you may find it a little bit special that many models satisfy this, but in fact, it's the case. As soon as there is a little bit of smoothness, so I'll write now some conditions, sufficient conditions, as soon as you can derive a little bit, you have this expansion. And this is very remarkable because then you may, actually this is how efficiency theory was then built, is that once you note that you have these expansions, and then in a sense, you are bound to analyzing the Gaussian case, what happens for this shift experiment, and that's not straightforward, but that's, say, feasible because it's Gaussian, and in the Gaussian world, things are easier generally. Okay, and so once you have analyzed what is optimality in this model, if you have now a model where you have a remainder here, you may hope, and actually you can, build up and construct an efficiency theory. And so this was done in the last century, but it is a beautiful piece of mathematics, I think, to get the kind of an efficiency theory already in parametric models. Okay, so that's the land condition. And to state the parametric BVM, I'll just add just a few quite mild conditions. So one is testing T, which will probably look familiar. Actually, it's a much easier condition to state and to verify than what we had in the first, so last week, where we were dealing with nonparametrics. Here, we just want that we can find a sequence of tests such that the first type error vanishes, just vanishes, and the second type error, so the soup, so if you go a little bit away, so complement of a ball around theta 0, so for any epsilon, you want that the error of second kind is also vanishing. Okay? So that's to handle the points that are far away from theta 0, and the points which are close, essentially, you can deal with this. So there is still a gap, because you see that here is only epsilon, but there is a neat argument showing that, in fact, in IAD models and in the parametric case, you can go from this neighborhood actually to a sort of almost 1 over square root n neighborhood. Okay, so that's a little testing condition. And finally, so just let me introduce still a couple of quantities just to make the statement a little bit easier to state. So Fisher information at theta naught, L theta naught dot of xi, and a centering Tn, which will be theta naught plus delta n over square root n. Okay, and quite useful notation for the next two lectures, for this lecture and the next, will be a shift, so very easy function, a tau, shift and recentered at Tn. So just the map that takes x, and so we just shift and rescale essentially. So we shift around Tn, sorry, and then we rescale by square root of n. Okay, so this is just to look with a magnifying glass at the right scale and at the right place. Okay, so that's just a notation, and the theorem is as follows. So BVM in the parametric case. Okay, so suppose you have that the model is LAN at theta 0 plus testing condition T. So LAN, of course, we assume also that I theta naught is positive. So sorry, actually it's a bit more compact to write it this way, the same. And I'll also assume something on the prior, of course. So we saw that if we put no mass around theta naught, we cannot hope to recover it. So I'll just take some density with respect to Lebesgue measure, and I just assume that pi theta naught is so that pi is continuous around theta 0 or on the whole, and pi theta 0 is strictly positive. Okay, so that by continuity, you know that on a little neighborhood you have mass, you have positive mass. And then what you have is that the posterior distribution, here I push it forward, I use the push forward here with this shift and rescale just to be at the correct center and scale. So the center is this Tn, and okay, I get this distribution minus n0 inverse Fisher information, which you may recognize, so that's sometimes called the Cramer-Rao bound, or the Cramer-Rao, yes, the quantity or bound. So the total variation distance between the shifted and rescaled posterior and the Gaussian, the optimal Gaussian in the sense of efficiency, goes to 0 in P0 probability. Okay, this is still random because it depends on x, and it goes to 0 in P0 probability. Okay, so that is a kind of a much more general statement, but it generalizes a Laplace result for the binomial model. Okay, and the conditions are pretty mild. All right, so we have this this statement. So why is that interesting? So one main implication of it is that, an important one, is that it implies automatically that certain credible sets are confidence sets asymptotically. Yes?
I did not understand even when reading the notes, what is this L dot?
Yes, so here it's defined, it's slightly informal because you can assume that, I think in the notes I said at some point you can assume that it's just a differentiability. Say you can assume, for instance, that for any x, because it depends on x also, for any x, the function that theta gives L theta of x is differentiable. Okay, and then it is this partial derivative with respect to theta.
Yes, but theta is multidimensional. I'm very confused.
So then you just get the gradient. So it's a gradient.
Oh, okay. So yeah, okay. The notation was uncommon to me. And also, I have a question for the practical use of Bernstein formula.
So for now, it's just abstract. It's just a nice asymptotic normality result, and now this consequence will be. I think it's the main application. But go ahead.
It was just about the fact that here you have the normal with the Fisher information at theta 0.
Yes.
Does it hold true if you replace theta 0 by an estimator of theta?
No, so that's the point, is that in the Bayesian, so that's a good point, that in fact in the Bayesian posterior doesn't have to estimate it. So in the frequency sense, what you would do is that you would get, for instance, maximum likelihood estimator, and then you would have to kind of, build your an interval, for instance, around it where you would plug in I theta naught. Okay. So here, if you like, you could replace this theta 0 by this, for instance, or by some other estimate. It would still be true. But what's kind of remarkable is that here it's it does it automatically.
Okay. Sorry for that.
No, that's a good point. Okay. So one important consequence. Yes. Yes, so indeed, it's just so it's just to give you a flavor of what's going to come next. But what's going to come next, I will drop this IID assumption. Okay, and indeed, in parametric models, also people have came up also with kind of more general LAN expansions, where here you just replace instead of taking the product, you just take P n. So just your likelihood, okay? So you can analyze this, you can extend this, but then it's a bit more complicated to write down this quantity. So that's why I didn't do it. Okay, just yeah. Okay. So let me just give the important consequences that let's do what I was doing in this picture. So let's so I will take the same notation maybe. Q alpha at x and q1 minus alpha over 2x be the quantiles. So here I'll say dimension 1. So p equals 1. You can also do things like this for larger p, but let me not go into that for now. Just in dimension 1 to fix IDs. So let's take the quantiles of the posterior, okay, in dimension 1. So really this picture. So the quantiles alpha over 2 and 1 minus alpha over 2. Okay. Then what you get is that if you have a BVM, so in particular, okay, it's a credible interval. So this, if I just do this, okay, given x, by definition, okay, here I'm assuming it's, so you can take also generalized quantiles if you are not continuous, but it doesn't matter much. Then what happens is that if you have BVM, that implies that actually it is a confidence interval. So if I call this again I of x, the probability, the frequentist probability that you are in I of x goes to 1 minus alpha as n goes to infinity. Okay, so that's one reason we like, so one reason we like these results is because it gives you a shape of the posterior, it's Gaussian, so it's a bit like in the CLT, and also because you have this remarkable consequence that certain credible sets are confidence sets. And you can check that in this case, from using this result, the confidence set you get is optimal also. It will be like frequentist optimal in the sense of efficiency. For those who know efficiency. Okay, great. So far, so good. Any other questions? Okay. So now what we'd like to do is to, of course, in these settings I talked about, we were not in a parametric setting. There was, for instance, the distribution of this survival time t was arbitrary, so it was a nonparametric model. So we'd like to deal with such situations, and those situations are called semi-parametric. And semi-parametric, what does it mean? Informally, it means that you are interested in a, so it can mean, can have various meanings, but one simple meaning is that you are interested in a finite dimensional aspect, so like a functional, like the median survival. It can also mean that you are interested in this more functional result, just a more general functional, which is like function valued. But the reason, so here we call it this because actually there is a rate square root of n here. So I will not define precisely what I mean with semi-parametric, but BVM for functionals. So we'd like to, I'll just talk about functionals in general. So we have semi-parametric SP setting. Okay, so again, so we have our model. So now I'll index it by eta because the parameter can be either a certain theta. Well, I'll give just two examples. You can have like a pair of parameters, theta comma f, for instance. So that's why I didn't call it theta. So again, we're in the dominated framework, and I denote by ln the log likelihood. Okay. So what we're interested in is a certain functional from the model into, say, R for now, a real valued functional, which is psi of p. And an abuse of notation, which I'll make, say, immediately, is that I'll actually often denote by the same, so this is the abuse of notation, the functional which actually maps from the parameter set to R, and since I have identifiability of the model, I can do that. I always assume implicitly identifiability. So here, alternatively, I can just look at this map, okay, which I'll denote psi of eta as well. Okay, so just two examples to fix ideas, and we also consider the first as a kind of recurring example. So eta, say, is a function, like a regression function or a density, and psi of f is, for instance, a linear functional. And linear functional will be actually quite central, and the reason is that those are, in a sense, the simplest functionals, and they will be building blocks for later, for tomorrow. So we'll consider this example, and another example is like more traditional, traditionally what's called separated semi-parametric models, where you are interested in the model has like two parts, like one finite dimensional part, suppose it's in R, for instance, and a nuisance part, something that's called the nuisance, although it can also be of interest, for also be interested in estimating it. And then the functional, the semi-parametric functional would be just the theta part of the model. Okay, so in the Bayesian setting, what we do is that we put a prior pi on eta, okay, and this induces, by push forward, this induces a prior, and so this induces first a posterior on eta, okay, as usual, the pi, which we denote pi dot x, and this itself induces a posterior by push forward on psi of eta. Okay, so that's something that was like the distribution of the crosses here. Okay, and so that's the push forward under the map that which will be just so I can p dot given x circ psi minus 1. Okay, and then we may want to just maybe here, let me see, okay. Just erase that. We'll just introduce a notation for centering. This tau that I was using here will have the same here in this context. Tau will be take a eta and go to square root n psi eta minus a certain Cn. Okay, so Cn will be a certain centering that depends on x. Okay, that we have to choose. All right. And so now let me just extend a bit this. So we say that, important definition, we say that so square root of n psi eta minus Cn under the posterior. Okay, so that means the posterior distribution induced on this converges weakly. So in the sense of convergence of distribution in P0 probability to a Gaussian N0 V if, so now for certain reasons I'll talk about a bit later, I'm going to weaken a bit this total variation statement. So the central limit theorem, we generally just take convergence in distribution, but you could also state it in the stronger and the slightly stronger assumptions under total variation. Here I'll just take a distance metrizing with convergence. So here, for instance, I'll take the bounded Lipschitz metric on R. Okay, so this between, so this induced posterior circ, so I take tau minus 1, so this tau, and N0V goes to 0 in probability, P0 probability. Okay, so that will be the meaning of the so right, it is say the natural generalization, okay, of this. So we are still talking about real valued functionals here, so or RP valued functionals. So I mean, this is relatively natural, okay. And now here on the board, I'm going to write what I will call a generic LAN setting. So we call this local asymptotic normality from before. And here, before I actually write it, I'll anticipate two questions that you may rightfully have. The first question is it really a generic setting? And the second question is, can you check it effectively? Okay? And in a sense, I claim that the answer is, in good part, yes for both. But for now, I ask you to trust me on this. So I'm going to, it's kind of an abstract set of conditions. And the important thing is not really exactly to understand really like kind of I think it's important just to have the idea and to see how it generalizes the conditions we had for the parametric BVM for now. And then okay, so let's view it like this. So I call this, this will be like assumption A, setting A. So we are going to assume that we can find, so assume that one can find a Hilbert space H equipped with some dot with some inner product, which I'll denote L, like LAN inner product, and the corresponding norm I'll write with an index L. Okay, such that so for suitable, so first thing for suitable etas. So to be specified below in the last part of the assumption. So for now, it's just like a certain writing, so that the log likelihood. So I'll write something which is similar in spirit to the local LAN expansion, to the LAN expansion, sorry, that we had before in the parametric setting. So a quadratic part. Eta minus eta 0 L squared. So already when I read that, here I implicitly assume that this can be embedded into the Hilbert space. Okay, so for this suitable etas, in particular, they need to belong to the Hilbert space. So this may not always be the case, so you have to take this with a pinch of salt, in the sense that you may have to adapt slightly this if your model maybe has some complex normalizations coming in. I'll give an example a bit later. Okay, so this is the quadratic part, and then the stochastic part, Wn eta minus eta 0, plus some remainder Rn eta 0. So for now, it's just a notation. I didn't say, apart from this, I didn't assume anything. The assumption will come. So here, I have to say what this W means. So this will be a random map. So I assume it's linear. And that I have something that I had also over there, although I didn't comment on that. That Wn, so I had this renormalized sum of IAD random variables, so there is a CLT and would converge in distribution to a Gaussian, and here I assume the same for this W. So I assume that Wn of H goes in distribution to N0 with norm the L squared norm in the LAN sets, okay, this norm here. Okay, so that's for the likelihood. I have to assume also something on the functional. So I'll assume that for some psi naught in H, we have the following expansion. let me try to write it on a line, psi 0 in H, we have that psi eta minus psi eta naught is equal to psi naught, so you could view it as a sort of risk representer, eta minus eta naught plus eta eta naught. Okay. And in the final assumption, we assume something on these remainder terms. And okay, so let's do that now. So for a sequence of sets an, such that, so that's where we can use the tools from the first week, such that pi an given x is 1 plus little o p naught of 1. So often we'll take an to be just a ball of reduced epsilon n around the truth. Okay, so we'll just, if we have a convergence rate of epsilon n around the truth, we'll have our candidate set an here. Okay, such that for eta t equals, so I have a certain path here. So sometimes you may not always be able to take a linear path, so you may have to adapt this. So we'll see in density estimation how we do that. Okay, so for a certain path, eta t, we have that the sup for all etas in an of these remainder terms, so n, so let me put first actually the t square root n eta eta 0 plus n eta eta 0 minus n eta t eta 0, where eta t is defined here. So this has to go to 0, little op0 of 1. Okay, so that's the setting. Fortunately, I could fit it in this board, and maybe it can stay here. So what is the intuition, which I already a bit outlined while I was writing? So this is the first part is like the LAN type expansion, where I will have to assume something on the remainder term. This is something concerning the expansion of the functional. So maybe, so for instance, if it turns out that the functional is linear in terms of this inner product, this will be 0. Okay. And finally, I need these sets an on which, because certainly this will not be true uniformly over all parameters, I want to localize in a sense. But the difference between this and the parametric setting is that in the parametric setting, you are able here to localize essentially in the neighborhood of size just a little bit bigger than 1 over square root n, whereas here you will have typically a neighborhood of size epsilon n, your nonparametric convergence rate of your posterior in a certain sense, okay? And you want to control the remainders. So it's kind of an abstract, so that's a remainder. This last part is a remainder term control, terms control. Okay? So in a sense, this is a sort of a version also which makes the proof not too difficult, and it's a bit abstract, but then there are many settings where you can verify this. I'll just say a word about it in a second. So let me give the statement of the semi-parametric Bernstein-von-Mises result that we are going to use later. So here I'll define, maybe I'll keep it for later, define psi hat. So the notation is maybe not too good because in principle it's not an estimator, it's actually the expansion of any what's called efficient estimator. But so I hope you'll be fine. I mean, we'll be fine with it. So we can denote it tilde if you prefer. But okay, so any efficient estimator will be expanded in this way plus little p of 1. And by the way, I'm talking a bit, several times I mentioned efficiency. So if you want a very nice account of efficiency theory, you can look at Ad van der Waals Saint-Flour notes of, I think it was maybe 24 or 25 years ago. Saint-Flour, maybe 98. Okay. So, and if you don't know it, doesn't matter too much. Whenever I say efficiency, it can mean for you that okay, it will just you cannot improve on it. It's optimal. The constants are optimal. Okay, so let me define psi hat like this, and V naught is psi naught L squared. This is actually the analog of the inverse Fisher information or the Cramer-Rao bound. And so the theorem is as follows, is just as you can guess. So it's just if the assumptions, so there is still one assumption, an important one, so semi-parametric BVM theorem. So let pi be a prior. So that's the joint work with Judith Rousseau, which itself built on a few previous works we did kind of separately. So let pi be a prior on eta, and suppose A. So these conditions on the board over there, and that you have the following condition. So for all real t, we have that certain ratio, so E ln of eta t, where eta t is the path over there, d pi of eta, divided, so it's an here with the set ans over there, E ln eta d pi eta, that goes to 1 in P0 probability, okay, as n goes to infinity. So if you have this, so that I will call condition C, like change of variables. Then you have that the posterior distribution of induced on psi eta recentered by this quantity psi hat given x. This goes in probability, I mean in the sense, which is still over there, to a Gaussian 0 and a variance V0. Okay. V0 is as n goes to infinity. Okay? And so, again, what's nice with this type of result is that if you believe indeed that this is the efficiency bound, then you get an optimal result, and you also get that Bayesian quantile credible sets are optimal confidence sets. So in particular, you can fit in this type of setting here. Okay, so there is quite some work here involved because you need to control this functional. There is the survival model, but you will be able to deal with this type of things. Okay, so any questions? Yes?
As regard the sets AN that you include in the function for the Bayesian property, are they supposed to depend on theta naught, on x?
So as yeah, I just said indeed. I just said it quickly while I was writing. So the typical set you consider here is just a neighborhood of theta naught, on which you can prove that you have posterior concentration.
Okay,
and so typically you.
It may depend on theta naught.
Yes, but it is just so you can use the tools of the first week where we prove the convergence at radius epsilon n to, yeah, sure.
Thank you.
Yeah.
Maybe you have already mentioned that, but here you assume that your Pareto space is H, or?
So I assume that I can embed it in the H, yeah, that it's included in the H, yeah, which may not be the case in general. Okay, so you have to. So this is why I said that you can take this with a pinch of salt. So for instance, in density estimation, I'm going to explain how this is kind of, there is just a slight variation on it. That for the path you have to change slightly the path. But
so your parameter space does not have to be necessarily an inverse space? You have
no. You need to be able to embed it, yeah, sure. So yes?
So can you repeat why psi hat is psi of eta 0 plus something?
So that it's just a definition.
Yes, but why is it natural to add something?
Why? So this is just because, so if you look at what is the limiting distribution okay, so if you have an estimator, for instance, you favorite one like the MLE or whatever, or a Bayesian point estimator, a good thing would be that it satisfies like a CLT, and here it will, because you get this, and this by definition over there it goes to a normal 0 V0. Okay, but what I said is that, so this is not an estimator, it's more like a technical device that we use here. So this is the theoretical centering, and in practice you may have a different centering. But to say, this is just saying that the posterior distribution will be automatically centered around the correct point, okay? And this is kind of the expansion of, so any estimator, so this is not an estimator because it depends on eta naught, but any estimator which will be optimal, efficient, will have this type of expansion with a little OP of 1. So in fact, little OP of 1 over square root n. So in fact, you will be able to replace this by this, so you can replace this in this result. That's a good question. By any, it's called linear efficient, is any estimator that has this expansion plus this linear efficient estimator. Psi tilde of x. This is a real estimator. Okay. Yeah. Thanks. Thanks for the question. Great. Other questions? Yes?
At some point, I think that you mentioned that the condition C was a kind of change of variable condition.
Exactly. Yes.
And,
there is no reason. There is no reason for that for now. To call it this like this, because I haven't explained it yet. But I was going. So we can do that. Give the intuition now. Is that you see? So you have here you have a shifted eta. So if you think of Cameron-Martin, so for instance, if you have a Gaussian process prior, you see that if here you have a GP here, and if this belongs to the RKHS, you are going to be able to do a change of measure here. Okay, and therefore it might be nice because then you may be able to So if formally you do the change of measure, you call this eta prime. Of course, there is a change of measure term here, but if you can control it and also control what it does to the set AN, intuitively here this is kind of the same, right? If you replace formally this by eta prime, and if you believe that you can control the change of measure term, that is close to 1, then this will be 1 essentially. Okay, so this condition is saying that so that in a sense the prior shouldn't be too sensible to a shift into this direction by the scaling 1 over square root n. Okay. Great, but that's an important point. So thanks. Indeed, I didn't comment yet on that. So there are 2 points, as I said. So why is it generic, or can we apply it in situations? I mean, you can guess that maybe we can apply it in white noise because it's kind of in white noise. In fact, we'll have just this term will be 0. And the other question is how we verify the assumption. So let me just quickly say a word about the situations that people have looked at recently using this framework. So you can do essentially, so all the models I've mentioned so far, so of applications, and so essentially it is where A in some form, you may have to change it slightly, is verified, and you can apply also this type of framework, is so all the models we have seen so far, so the Gaussian white noise, regression, density, etc. So you have the survival models. So essentially, since LAN is very natural and common, you have the Cox model. Just know a bit about it. So you can do inverse problems. Inverse problems, like also related to observing a noisy solution of a PDE. There is quite a lot of work by Richard Nicol and co-authors in this setting recently. Also, you can do causal inference. So, like, if you want to estimate the average treatment effect, for instance, there is a nice paper by Ray and van der Waart on that. You can do diffusions. I mean, there are many settings where you can do this. Okay, and in a moment, so now I'm going to give a proof. The proof you'll see is not very hard because we kind of essentially just what you need. And then we'll see how we verify it in the example for Gaussian process priors. Okay, so if you have any question before the proof, but you'll see the proof is not too difficult. It's just manipulation of the quantities we have introduced, essentially. And then, of course, the hard work is proving that this type of condition. So where you have quite a bit of work is in proving is often that the remainders will be under control. So you have to choose wisely your set n, and then also the change of measure, the change of variables condition. Okay, so the proof. So it's enough to show that we have that the posterior. So we can concentrate. The first thing to notice is that we can concentrate on the sets. I can put an indicator here. An indicator given x n0 v0. And the reason is just that because the other term with the indicator of the complement, since the posterior of the complement will go to 0, the probability that it's non-zero will go to 0. So I have a term, the other term goes to 0 in probability. Okay, so I can focus on this. And the way we do this is that we show that Laplace, him again, transforms converge, okay, because that's enough for convergence of distributions. So we'll show that e to the exponential, so t square root n, so t is just a variable in the Laplace transform, psi eta minus psi hat. So here I have my indicator of an, which in a second I'll pull outside the exponential, given x. So we want to prove that this goes to exponential, so the Laplace transform of the Gaussian, v0 over 2. Okay, so here I actually, when doing the proof here, I'll assume that I'm in dimension 1. Okay, so that dimension 1. So this here, I can just rewrite just this exponential with the indicator inside. I'll just write like the exponential itself, minus psi hat, indicator an, and if I'm not on an, I just get 1, okay, because I have 0 inside the exponential, so it would be an complement, okay? And I want to show the expectation given the data of this, and here you see this other term. So when I take the expectation under the posterior, I just can, this term will be handled with, so here e given the data, plus e given the data of this. So this is just the the posterior probability of the complement, okay, which goes to 0 in probability. So this term I can forget about. Okay, so now let me just write this. So this is just by definition by the by Bayes formula. And the reason why Laplace transforms are so nice here is that it puts everything at the exponential level. Okay, so I have t square root n psi hat minus psi eta, sorry, minus psi hat. Okay, so that's the first bit, and then there is the likelihood. Okay, so ln, the log likelihood, because I put it in the exponential. And here I write something like this. I'll add a term in a moment. D pi of eta divided by, so here I have only exponential ln of, I just have my likelihood, and I'm going to add a term in a second, d pi of eta. Okay. Well, here I actually will not add a term for now, times this. And here what I'm going to add is ln of eta t plus ln of eta t. Okay, like this. And now I can use my expansions, okay, because here I can use the functional expansion, and here, so sorry, the likelihood expansion, and here I'll use the likelihood expansion. Okay, so let's do that. Okay, so what we have now is that we can use the setting A to write that, so ln of eta minus ln of eta t is ln of eta minus ln of eta 0 plus ln of eta 0 minus ln of eta t, and I can use these expansions here. So I get minus n over 2 eta minus eta 0 squared plus n over 2 eta t minus eta 0 squared. I get the stochastic term, which is linear, so I get now square root n w eta minus eta t, wn eta minus eta t, and a remainder, which is, which I'll write here, so Rn, exactly what I have here, down here, if I didn't change the signs or something. No, I think I put the correct sign. Eta t, eta 0. Okay? And here, this one, I can just use, I can just expand. So eta t now, remember that it's given by this. So the eta minus eta 0 term will cancel. Okay? So since they cancel, I just don't write them. And I have a quadratic term which comes from this one here, which gives me t squared over 2 norm of psi 0. Okay, so that's the good guy, okay, because it gives me the v0. And then I also have the cross term, which is given here by, so there is a minus, so it should be minus, and so there is a square root t square root n twice, but there is a divided by 2, and then I get the Lan inner product between eta minus eta 0 and psi 0. Okay? Okay. Great. So far so good. So now we'll deal with, so that was the first bit. Then the second bit is we are going to expand the functional here. So we know that t square root n psi eta minus psi hat is equal to what? So I just use this expansion now. So it is t square root n I insert minus psi eta 0 plus psi eta 0. Okay, so I get psi naught eta minus eta 0, the remainder term. That's for the first bit, and then the second bit is minus psi hat plus psi eta 0, so it's minus Wn psi naught divided by square root of n. Okay. Right, and then we are done essentially. So because now I wrote, I mean, we're not done yet, but we are done with expanding. So now we just put together the two expansions. So just the sum of both. Okay, so there will be, in principle, there should be some simplifications. So they will, so eta minus eta t, so this is what? Is t psi 0 divided by square root n. So you see that it will cancel this one. Okay? So if you allow me to cross here, this will cancel this one. And then this is canceling this one. Okay? And so finally what I get is that this is integral over an of exponential, so the good, what I call the good term, which is just the Laplace transform of the Gaussian. And then I get just remainders. Okay? So plus something which I know I control, which is just what on the board on the right hand side I have assumed I have control on. Okay, so plus t square root n eta 0. So that I control uniformly. D pi eta. Okay, so this in absolute value with the soup, I know it is a little op not of 1. Okay, so I can remove, and then divided by the whole integral over the log likelihood. Okay, so that keeps the same, and here I forgot to write this term in yellow plus ln of eta t, so let me, okay. And now, so what I do is that this term doesn't depend on eta, so I can pull it in the front. This is controlled, so I just get the term from my change of variables. Okay, so quite easy, relatively easy proof. So just setting what you need. So here there is a 1 plus little op naught of 1. And here it's the ln eta d pi eta. Okay, and by C, this goes to, so I forgot to put the term here, e to the t squared over 2 psi 0 squared in the land norm. So this goes to e t squared over 2 psi naught L as we want it. Okay. So this proves the result. And now, of course, comes the question of whether how we can verify this type of assumptions. So I don't know if there are any questions. Yes?
Yeah, I'm a little bit confused about this change of variable.
Yep. So
about its interpretation, because can you interpret so on the denominator it's the conditional distribution of eta given x? Basically, the conditional density.
Well, no. In the denominator is the marginal. It's the marginal density of x in the Bayesian world. Yeah. So here, what I'm just saying, I hope it will become maybe more clear with the Gaussian processes example. What I just say is that if you have this shift under the prior so this eta t is just a shift, okay, and so but it's a shift divided by square root n, okay, so it still is vanishing the quantity that you add. So if your prior is not too sensible to this shift, in the sense that maybe either you can change measures or so of course with GP we know that if you are not in the Cameron-Martin space, you in the RKHS okay, it can happen, and we'll see. What you do then is just that you approximate by a sequence of elements in your RKHS, like we did in the first week, and then you can do your change of measure within this approximation, and you have to control the rest, okay, the approximation quality. So this means that for GPs, there are simple tools to kind of replace this by an eta tilde, d pi eta tilde. And so if you believe me that this will just be e ln eta tilde d pi eta tilde, then this just becomes, again, this will just be pi of an given x, which we know goes to 1. Okay? So that's the intuition. Okay. All right, other questions? So let me give some examples quickly. So the white noise model is really the simplest one. So it's really when I was talking about the parametric BVM, and I told you, okay, in the LAN expansion, if you have just a Gaussian shift experiment, then the remainder is 0. Here is exactly the same. Just that in infinite dimensions, the Gaussian white noise is just a shift experiment, and then you have this LAN expansion with 0 remainder. So that's kind of the most favorable situation. So in the Gaussian white noise model, so it will be also similar in Gaussian regression, you have actually that, so eta is equal to f, and actually the LAN norm, we'll see in a second, is actually just the L2 norm. Okay, and here I'll interpret the white noise just for simplicity, I'll interpret it as the sequence model, so projected onto a basis. Okay, so here what you have is, so f in this setting is just viewed as a sequence of its coefficients into the basis. Okay, so it's just, so the difference is just going to be equal to exactly minus n f minus f naught 2 squared. So that's why I said that the LAN norm is L2 plus square root of n, and here you don't even have to take the limit, is w, a certain w f minus f naught, so I'll not define precisely what, I mean, I can write precisely what it is. It's just, there is no need to put any index because you are already in the limit. You don't have to, okay, so you don't have to verify this convergence as n goes to infinity because you are already Gaussian. Okay, so this, why do you have this? It's just Cameron-Martin formula. So WG is just the usual change of measure term, which is, here you can write as, so in terms of epsilon here, you can write it as GK epsilon K. Okay, and then therefore the remainder term is just 0, well, which is great, okay. No need to work too hard in this model. And then, say, suppose we look at a linear functional, okay. Then we also have immediately that, okay, so psi f minus psi f0 is just the integral of a f minus f0 plus 0, okay. The term here is 0. Okay, so far so good. And then the theorem, so the semi-parametric BVM implies, gives the result as soon as, so it's enough to take, so you can state a little theorem. So if pi contracts on an, contracts on an, okay, so which is this assumption, and as I said, often you will just assume that an is just included, say, in a neighborhood of size epsilon n of f0, the L2 norm. So here it's nice because it's really the L2 norm. If you have this and the change of measure, so what I called, or the change of variables, what I call change of variable condition, which is C, then the semi-parametric BVM is okay. Okay, so you only need to verify this, these two conditions. So here it's very nice. Yes.
I don't understand that you consider the sequence model.
Yes.
Or
So you can also write it in the other version of the model. Then you have like the Giazanov Kahneman-Martin formula. So I mean it's the same. So except that you have a stochastic integral in one case, and here it's just you have this this infinite sum of Gaussians.
So psi f is you should write it as a function on sequence.
Yes. So here, that's right. Thanks. So here, sometimes I kind of abuse a bit notation, but okay. Thanks. Okay, but it is also this. Okay, and this as well. Okay. So okay, sum of ak fk minus f naught k. Okay, so let's move now to the, unless there are other questions. So let's move now to the density model. So in the density model, things are a little bit more tricky because you have densities. So you have normalizations. So here you'll have to, maybe to believe me that this is kind of the natural, what I'm going to write is kind of the natural thing. There are various possibilities actually. You can parameterize your model in different ways in the density model. But I'll take one for which we got the simplest or the weakest condition, which is that I'll actually parameterize it with the log. So I will write rather with eta the log density, log of f. And then assuming that also log f naught exists, so that f naught is bounded away from 0. So often in Bayesian nonparametrics, with the density model, it's kind of easier to have boundedness away from 0. Otherwise, you have some problems in the density model. So I mean, you can do it in specific cases, but for the general theory, it's a bit easier to be bounded away from 0. So in a sense, this log parametrization is a bit easier to work with. So I'll set eta to be the log of the density, log f. So here, this means that you have IID data. Okay, so here, pi f is just the law on, say, I do density estimation on the unit interval. So just the distribution which has a density f on 0, 1 with respect to Lebesgue. Okay, so if I take, so that's important, I take the log of f instead of f. So I'll have the following LAN expansion. So there is you can check that you have the quadratic term. So I'll write the LAN norm in a second. So here I'm just writing the same as on the right-hand side, I guess, plus the remainder term. Okay, and here, so then I need to introduce some notation. F naught of g will be the integral of g f naught, and f of g will be the integral of g f. Okay, and so if I have a certain g in L2 of f naught, so which is the set of functions g such that integral of g squared f naught is finite, then the LAN norm is going to be a recentered L2 norm. So g minus f naught of g squared f naught on 0, 1, if I have density estimation on 0, 1. And w naught of g, this time it will not be Gaussian, it will converge to a Gaussian. It's just 1 over square root n, so a quantity to which you, when you see it, you want to apply the CLT to it. Okay, so it's just an empirical type quantity, which is n recentered. Okay, so that's okay. So you can always write it like this. So this is also, by the way, just this is a log density. So since we have IID data, is just eta minus eta naught of xi, and you may rewrite it this way with a certain remainder term, which I'll not write, which is just the difference between what's here and what I've introduced. But you can check that this is kind of the right way of in which the will be small. Okay, and so the functional expansion now. So suppose we have the functional. So suppose we have there exists a psi tilde from 0, 1 to which is bounded, such that I can write psi of eta. Well, here I use psi f in the notes, I think, but anyway, psi of eta is equal to integral of psi tilde f naught, f minus f naught, plus tilde. So here tilde is not exactly the same as the which I wrote here, just because here it's not a bracket, it's not an inner product with eta minus eta naught. You still want to write it in terms of the Land norm. Okay, so it's another slightly different tilde. Okay, so that's just a definition, and the integral of psi tilde is 0. It's centered. F0, sorry. Okay, and so with the linear functional, so if I have psi of f or psi of eta, which is the integral of a f, then between 0 and 1, I have that psi tilde is just a minus f naught of a. So I subtract this f naught of a just to fulfill this condition. So f naught of a, again, it's just the integral of a f naught. Okay, so that will work well. And then tilde here is 0. Okay, and now I didn't tell you what the path here is on which I'll verify the remainder term condition. And here it's slightly, one has to be a bit careful, because we want to have a path of densities. So when you change the density here, it's not completely obvious that this, you have this, it's not, so you perturb the log of the density, and you still want this to be a density, eta t. So it's, in general, this will not be a density, so you have to compensate for it. But what is nice here in the density model is that, as you may see from the expressions here, if you add a constant, it vanishes. So if I take g plus a constant k here, it vanishes from this expression, because f naught is linear, f naught of k is k, so it vanishes. And the same here, if I add a constant k to g, it will vanish on both sides. So in fact, I can just here take a term which depends on eta, but is a constant in the space variable. Okay, so because here those are functions. Okay, everything is a function, but what I write here, this normalization term, is a constant, although it depends on f. Okay, but it's a constant. It doesn't depend on the space variable. Okay, and that's important because now, so this term just makes this a log density. So I work with the log densities, and so if I take the exponential, you can just see that I compensate exactly but what's needed to make this a log density. This is a log density. Okay, so and I write ft equals to e to the power eta t. This is a density by definition. So in principle, when you look at the path, it doesn't exactly fit this framework, but in fact, it does in the sense that if you do exactly the same proof of the theorem that we did here, and now with this path, you'll see that the constant vanishes because of this definition of the Land norm and the W term. Okay? So you are allowed, so this is already a slight twist compared to this exact setting. Okay? So you can check it, I'll not enter into details, so that I mean, it's just, as I said, it's just that the constant vanishes. So then you get a density estimation theorem so you can apply this theorem, and in the notes I give a slightly different version where, I mean, it's almost the same except that I'm a bit more specific on the set A, and you don't have actually to check. In density estimation, it's quite easy to check that this will be small for certain ANs, and then you are just essentially bound to have a condition on R tilde, okay, on the non-linearity in this sense of the functional. So the statement is in the note, but maybe since lunchtime approaches, let me maybe just give rather an idea of how you can check these things for Gaussian process priors. Yes?
I wouldn't understand why do you make these assumptions on the functional group, because it's not the same assumption as, you did, if I understand correctly, you don't translate the assumptions here, because if you translate the assumptions you have in the general...
Yes, so if I want to make this correspondence, I have to say that this is the Lahn norm, which is written here. So this will be psi naught, and this can be still psi tilde, in fact. Eta minus eta naught, plus something, which is just the difference, okay, plus some term b. Okay, and what I need to, within this framework, I need to work with this one. Okay.
And what do you make these assumptions?
Well, this was just because for later, what I'm really interested in is not a linear functional on the of the log density, but of the density itself. Okay, so here I should. That's why here I should rather write it this way. So in fact, yeah, sorry. So this was misleading, I think. So what I'm really interested in for later is a linear functional of the density. So it was not psi of eta. It's not a linear functional on the. Okay, so this is not necessarily for a linear functional. So I can just assume this, but you're right. So here it was more for the f. But the reason why I write it this way is because although I use the eta parametrization, what I'm eventually interested in is in linear functionals of f itself. Okay.
This is because people want to consider this kind of...
Yes, but because I want to do that. And why do I want to do that? Is because next time we'll move to a world in which we, so remember here, so this is like the primitive of the density, the distribution function. Okay, so to study this subject, it will be natural to know things about linear functions of little f, not eta. Eta here is okay. But you're right. Yeah, thanks. I should use psi of f. Okay, so let me maybe quickly in the last maybe 5 minutes or so. Give some insight about the verification of this condition for Gaussian process priors. So philosophically, it's kind of, this should be natural, right? So this shift should be quite natural for GPs because we have the tools with the RKHS. We know that we have the nice Cameron-Martin change of variable formula, which gives us really a precise control on the change of measure term. And if you don't have a Gaussian but another object, then first it's not so clear how you do the change of variables, and then you may have to do it by hand. Okay, control it. It's possible for certain priors, but you have to work more. So what's nice with GPs is that you have a kind of a compact way of verifying the assumptions almost directly. You have to work a little bit, but so just recall. Okay, so in terms of set AN, that for GPs the rate in a suitable distance is not so clear. Actually there will be the Lahn distance. It's not so clear whether it's a testing distance. Actually, often it's not a testing distance. But in simple model, it can be, like in white noise. But, so the rate is given by something like this for GPs that we saw last week. And so to fix IDs, consider the Gaussian white noise model. with a Gaussian process prior on, so here again, just simple, okay, and it's just L2, okay, and we have the following theorem. So let pi be a GP. So again, it's in white noise, it's quite specific, but you may apply it much more broadly to the interest of these tools is that they don't need the specific model. Of course, you need to check the assumptions, but on L2 with RKHS H, okay, so suppose epsilon n verifies this equation, the rate equation. So here is a concentration function of the GP in the Banach space, in the Hilbert space L2. Okay, with for the as we introduced last week, with for some f naught, okay, in L2. Suppose that A holds. Okay, so the land type. So A holds. So we in Gaussian white noise we've seen it's kind of obvious, but we need to specify still the AN set. F, so we take just an something included into an L2 neighborhood, and we have seen in the first week techniques to prove that the posterior concentrate there. And the main assumption here is, so there is no reason why your psi naught, so if you in the white noise model, we have, okay, so we have seen, for instance, for a linear functional, we have, so if you look at just the linear functional, okay, so it's just A f minus f naught, but there is no reason why this A should be in the RKHS. Okay, so if it's not in the RKHS, doesn't matter. Let's take a sequence approximating it. So there exists a sequence in H, and the rate zeta n going to 0, such that we have a few conditions. Psi n approximates psi naught in the L2 norm. So in general, you would check it in the land norm. First thing. Second thing, so we want the RKHS norm, although it can blow up, we want to control it still. It's more than square root n zeta n. And finally, we want square root n epsilon n zeta n to be a little O of 1. Okay, so we have a theorem for GPs, and if you do, you can do more or less the same in density estimation, where of course you can take a GP as a prior, but you do this exponentiation and randomization. You have a random density, and you'll have more or less the same theorem also in density estimation. Okay, so the notation will be a bit different, but again, the things will be of the same flavor. So this just says that you approach psi naught in the RKHS, okay, and this is what sometimes called the no bias condition. And just maybe in 1 minute to give the intuition, it's just that, so since you introduce this psi n, so here in the, so this path here is eta minus t psi naught divided by square root n. So here, if I know that psi naught is in the RKHS, I just change measure directly with the Cameron-Martin formula. I get an extra term, which I haven't tell you how to control, but it's easy because there is the square root of n here that helps you. And you are more or less done. You just need to control this. But if psi naught is not in the RKHS, you do here minus psi n plus psi n. You do the change of variables for psi n, and you have to control the remainder. So how does this come from? It comes because you have eta, and in the likelihood expansion, you have eta minus eta naught, and then minus, and you'll have a term like t square root n psi naught minus psi n. Okay. So, and you'll have the land norm squared. So when you take the square, the cross term that you'll have here, and there is an n in front, n over 2. The cross term you get will be the land norm, which is here the L2 norm of eta minus eta naught. So that's where this epsilon n comes from. And you have the approximation part, which is where this zeta n comes from. And you have the square root n here because you have n in the cross term, you gain only a square root n. So that's where this comes from. And this, intuitively, it can be interpreted as saying that the RKHS approximation is still good enough and compatible such that this cross term doesn't annoy you. But so the difficulty here is that this is only a sufficient condition. It's obtained by doing Cauchy-Schwarz on the cross term, but it's kind of a delicate question to know whether this is necessary or not. And in fact, sometimes you can do a bit better than that, but that's kind of another topic. Okay, so I'll finish here. Sorry for going a bit over time, but so the purpose today was to show this generic semi-parametric theorem, and tomorrow we are going to try to lift it to infinite dimensions and to like functional statements, functional BVMs. Okay, thank you very much.